Welcome to The Explainer. Today, we're going to demystify something you literally interact with every single day, even if you can't actually see it. We're talking about electric charges and fields. If you've ever wondered what holds the physical world together at the absolute most basic level, well, you're in exactly the right place. We're going to break this whole thing down right from the ground up.
Okay, let's dive into this with something you've probably experienced, 100 times. You run a plastic comb through dry hair, and suddenly, boom, your hair is standing on end, kind of magnetically reaching out for the comb. So why does that actually happen? This super relatable everyday phenomenon is basically our perfect gateway into the world of frictional or static electricity. Just by rubbing two everyday materials together, you've somehow awakened this dormant, invisible power. But, humanity's understanding of this little trick didn't actually start with plastic combs.
To really grasp this, we've got to look at this as an amazing historical detective story. Way back in 600 BC, the ancient Greek philosopher Thales of Miletus noticed that rubbing a piece of amber with wool made it attract stuff like light feathers. And get this, the Greek word for amber, it's electron. Fast forward a couple thousand years to 1600 AD, and William Gilbert, he was actually the doctor to Queen Elizabeth I, started studying this stuff systematically. He coined the term electrica. And then finally, in the 1700s, Benjamin Franklin came along and gave us the terms positive and negative to describe these charges. Now, what's really, really interesting here is Benjamin Franklin's little, historical oops. You see, Franklin's choice of what to call positive and what to call negative was literally a coin toss. It was just a convention. But it turns out the tiny particle actually responsible for all this electrical flow, the electron, ended up being assigned a negative charge under his new system. Actually, mathematically speaking, it would have been way more convenient if electrons were positive. But hey, in science, sometimes we just have to live with old historical mistakes. So electrons are strictly negative. So what actually is a charge anyway? Well, think of it as a built-in feature of the tiny building blocks of the universe. It's what we call an intrinsic property of elementary particles. This means that literally all matter, you, me, the screen you're watching this on right now, it's all made of atoms, which contain positive protons and negative electrons. It's the very nature of these tiny elementary particles that gives rise to the electric force between objects. It's just a fundamental, unavoidable feature of our universe. And that brings us to the absolute golden rule, the fundamental law of electrostatics. It's incredibly simple, really. Like charges repel and unlike charges attract each other. Two positives, they'll push away from one another. Two negatives will do the exact same thing. But a positive and a negative, they will aggressively pull together. This one single, simple concept of attraction and repulsion, it basically drives almost all the electrical behavior we ever observe in the physical world. Let's jump back to our comb and hair for a second and look at the electronic theory of frictional electricity. When you rub two objects together, you aren't just creating a charge out of thin air. No way. You are physically ripping electrons off of one object and transferring them straight to the other. The material with a higher work function, which, by the way, is just a fancy physics term, meaning it holds on to its electrons a bit tighter, that material steals electrons from the other one. So one ends up with an excess of negative electrons, and the other is left with a deficit, making it positive. That physical imbalance? That's exactly what we call static electricity. But wait, why doesn't this work if you, say, rub a metal rod while holding it in your bare hand? Well, that all comes down to the difference between conductors and insulators. Conductors, like metals or even human bodies, they allow electric charges to flow freely. Insulators, on the other hand, like glass, wood, or your plastic comb, they hold on to those charges tightly, stuck in one place. So if you rub a metal rod, the charge just flows right straight through your hand. But if you rub a plastic comb, the charge is trapped exactly where you rubbed it, perfectly ready to attract your hair. Now, that idea of charge flowing through your body, that leads us directly to an absolutely crucial safety concept: earthing, or grounding. The earth is basically just a giant sponge for electric charge. When a charged body touches the ground, say through a specific wire in your home's electrical circuit, its entire excess charge safely passes into the earth, and the earth just absorbs that sudden jolt of electricity. This is exactly why your household appliances have an earth wire. If a fault occurs, that dangerous excess charge runs safely into the ground rather than, right through you. Okay, let's move on a bit and look at the strict mathematical rules that govern all of this stuff. First up is the quantization of electric charge. Now, I know that sounds super complex and maybe a little intimidating, but it really just means that electric charge isn't a smooth, continuous flow, like water pouring from a tap. No, it comes in discrete, countable chunks. You can't have half an electron's worth of charge. Just doesn't happen. Any charge on any object is always an exact whole multiple of one basic quantum of charge, which is a single electron.
The next strict rule we have to talk about is the law of conservation of charge. Charges can literally never be created out of nothing, and they can never be destroyed. Never. They can only be shuffled around from one body to another. If you look at an isolated system, or actually, if you look at the entire global universe, the total net charge remains completely, entirely constant over time. It just doesn't change.
To really appreciate how unique this conservation rule is, let's compare electric charge to something we all intuitively understand, right? Mass. Now, mass is always positive. You can't weigh -10 pounds. But electric charge, it can be positive, negative, or zero. Plus, mass isn't even strictly conserved. As Einstein taught us, mass can actually be converted into energy. But electric charge, it is strictly 100% conserved. It's this uniquely permanent property of our reality.
Now, right about now, you might be thinking, okay, charges are tiny, so these forces must be pretty weak, right? Oh, absolutely not. Wrong. The brilliant physicist Richard Feynman once had this amazing quote. He said, if you stand at arm's length from your friend and instead of being electrically neutral, each of you had an excess of electrons over protons by just 1%, the force of repulsion between you would be enough to lift the entire Earth. Seriously, think about that. Just 1%. That is absolutely mind-blowing. The sheer, terrifying power of electrostatic forces is almost beyond our comprehension, mainly because our everyday world happens to be so perfectly balanced and neutral. So, the crucial point is, how do we actually measure this immense force? Enter Coulomb's law. Back in 1785, Charles Augustin de Coulomb finally figured out the exact mathematical rule for this. He found that the force between two stationary charges is directly proportional to the size of the charges multiplied together, and then inversely proportional to the square of the distance between them. What does that mean in plain English? Basically, the bigger the charges, the stronger the push or pull. But the second you start moving them apart, that force drops off incredibly fast. It's essentially the electrical twin of Isaac Newton's law of universal gravitation. To put Coulomb's math into a bit of everyday perspective, let's look at the standard unit of charge itself, the coulomb. If you were to take just one single coulomb of positive charge and place it exactly 1 meter away from another single coulomb of positive charge in a vacuum, they would repel each other with a force of 9 billion newtons. Let me say that again. 9 billion. That's the equivalent of 1,000,000 tons of force, just coming from a single unit of charge sitting exactly a meter apart. It's wild. So here's the big question. How does this immense force actually cross that 1 meter of empty space? I mean, they aren't touching, right? This introduces a massive shift in how we view the universe, the concept of the electric field. A charge doesn't just sit there doing nothing. It creates an invisible electrical environment in the space completely surrounding it. So when a second charge enters this invisible environment, it's the field itself that exerts a force on it. To help us actually see these invisible fields, the genius scientist Michael Faraday invented a pretty brilliant visual cheat code. He called them electric lines of force. Basically, these are imaginary curves drawn through space. If you were to drop a tiny positive test charge right into the field, the exact path it naturally takes as it's being pushed or pulled around traces out what we call a line of force. It's literally a map of the unseen environment around us. And this brilliantly illustrates exactly how the physical world actually behaves. These field lines follow some very strict rules. They burst outward from positive charges and crash into negative charges. And, this is key, they never cross each other. Ever. They behave almost like stretched rubber bands. They really want to snap together and contract lengthwise, which beautifully explains why opposite charges attract. But they also expand and push each other sideways, which is exactly why like charges repel. Finally, wherever the lines are drawn closest together, that's where the field is at its absolute strongest. Now, when you place a positive charge and an equal negative charge right next to each other, you create what physicists call an electric dipole. And if you look at the field lines for a dipole, honestly, it's an absolute work of art. The invisible lines flow continuously in these beautiful sweeping arcs. They start from the positive point charge and bend perfectly around to terminate right on the negative point charge. It is just a gorgeous visual representation of tension and perfect balance in physics.
Now, as you probably know, physicists absolutely love to measure things, even totally invisible things. So we measure these fields using something called electric flux. Imagine the electric lines of force are like water flowing down a rushing river, and you dip a net into the water. Electric flux is simply the measure of the total number of electric field lines passing directly through that net, or that specific defined area. It just tells us exactly how much field is penetrating a given surface. And all of this leads us to the ultimate mathematical tool, Gauss's theorem. Now, I know the name sounds a bit heavy, but Gauss simply realized something amazing. If you imagine a 3D bubble drawn entirely around any amount of charge, the total electric flux bursting out of that closed bubble is directly proportional to the exact amount of net charge trapped inside it. It's this beautiful, incredibly elegant law that lets us calculate really complex electric fields with surprising ease. So, as we finally wrap up this explainer, I want to leave you with a pretty provocative thought. Everything you touch, everything you see, your very own body right now, it is all held together and kept apart by these incredibly powerful, perfectly balanced, invisible fields. So the next time you feel a shock from a doorknob or see your hair stick to a plastic comb, ask yourself, how are these invisible lines of force shaping every single interaction in the universe right now? Thank you so much for exploring this fascinating topic with me. Keep wondering and definitely keep looking for those invisible forces all around you.